welcome back. I hope you had a good lunch. Where did everyone go? What did you have? Noodles? Fish and chips? American. American. Japanese. Well, we are very multicultural in London. So Razvan's going to start us off for the afternoon talking about VoLTE, something I don't understand at all. VoLTE and IMS and WebRTC.
Yeah.
So I'm going to sit and I'm going to learn and pass it on to you.
Thank you. Thanks for coming here. Thanks for taking your time from lunch. Hopefully you will enjoy my talk. Who here has ever worked with IMS or have any experience? Well, so there are a couple of you that, great. So hopefully I can teach you something. If not, you can teach me anytime. But let's see. So today I will be talking about how you can enable, how you can get access to IMS features from using WebRTC. We'll first have like a small introduction about myself and the project I'm working with, then the architecture of IMS, and then I will show you what exactly are the components that you need to enhance in order to provide WebRTC access to IMS infrastructure. About me, I'm from Bucharest, Romania. I've been working with the OpenSIPS project for 14 years now, since 2010. I'm one of the OpenSIPS core developers and SIP Hub CTO, and I'm a father of a 3-year-old son. What OpenSIPS is, a SIP proxy or server. It is highly flexible, it is programmable, has a bespoke programming language. It is very, very flexible and very highly scalable, supports 20K calls per second. At least this is what we tested with. It may go higher with different hardware, millions of simultaneous calls, and that's because it only handles SIP signaling. It doesn't handle RTP. And it can be used in various scenarios as SBC, a front end to your VoIP core, your existing VoIP core, load balancer, residential scenarios, trunking, call center queuing, virtual PBX, whatever. It talks SIP, so whatever SIP application you have, OpenSIPS can help you with. And one of the setups that OpenSIPS can be configured for is IMS. For those of you who have not used IMS, it stands for IP Multimedia Subsystem, and it is generally operated by mobile operators. So you have your phone, you have a tower. The operators have their own database, subscribers database, right? So whenever you want to get into a network, you go buy a SIM card, or nowadays you can buy it online, an eSIM card, and then you are able to access the operator's infrastructure. So your phone connects to a tower. Your phone is here it's a UE, stands for user equipment. It connects to a tower, and then you have access to the operator's 4G network. So this is how you get the 4G connection, or 5G, or 3G, whatever. It depends on where you are, on what kind of services are being offered by your operator. And then, so this, at this point, you only have your 4G connectivity, but you also want to place calls, right? And before, actually, without IMS, your phones would go like through traditional switching, so it does not take the benefits of all these 3G or 4G networks. Well, this is what IMS tries to do. It tries to bring the calls over the IP network in order to benefit of all the improved or less latency, improved throughput, and all the stuff that the 4G or 5G network offers. So IMS basically it's just the voice or video part of your, let's say, mobile phone. In terms of implementation, it actually is a very complex architecture framework for delivering different multimedia services, not only voice and video. It can deliver any multimedia you want. And there are a lot of specifications that describe the interactions between all these components that are part of the IMS. It is modular and, it is modular and all the interfaces are open. And it basically allows you, for those of you who've heard, it allows you to do VoLTE on your phone. So on your phones, you can enable, there's a thing that you can enable your VoLTE features. This stands for Voice over LTE. It has been developed by One Voice Initiative in 2009, but it was quickly adopted in 2010. And it contains a lot of specifications about how you can build these components in order to provide voice over 4G network. The major improvements it brings over the traditional or 3G or 2G networks is you have a faster call setup, high definition voice quality, video calling that you couldn't do over traditional switching, and reduced background noise. As I said, it's a very complex architecture. This is a picture of it. So we have the core. This is the EPC core, provides the 4G connectivity. Then you have the IMS core, which provides voice and I'm not sure you see my pointer. You do see it, okay? And there's also a component that helps you communicate with other or older telephony systems, like TDMs, for example. But nowadays, we are talking about 5G, right? So 4G is different than 5G. 5G has been developed in has been released in 2020. So it is normal to bring voice support in 5G as well. This is what voice over new radio, voice over NR stands for, and brings a lot of improvements over the old VoLTE specification. It has better codec support, supports AMR wideband, faster call setups, lower latency capabilities, but it also, although it allows you to fall back to VoLTE, always fall back to VoLTE, well, because unfortunately you don't have 5G connectivity everywhere, but it drops the 2G and 3G support, so you can no longer fall back for a call from 4G to 2G or 3G. This is the new architecture. So here on the bottom side, we have the 4G architecture. Here we have the 5G architecture. And here we have the IMS. It's important to notice that the IMS is more or less, is more or less the same. It has the same architecture. It's just the interfaces that are being used. For example, for the 4G, we have this. This is like a diameter protocol interface. And here, 5G brings some new, new interface that uses HTTP 2.0. So, as I said, there are different core architecture, but the IMS architecture is the same. The only difference is the interfaces that are being used to operate with the core, either 4G or 5G network, and this is basically a difference between diameter and HTTP 2.0. And the fact that voice over new radio provides fallback to VoLTE, this is actually a mandatory requirement because, as I said, you don't always have 5G everywhere. So you always need to be prepared to fall back to 4G in order to have your calls active. That's why you always need to implement both of them. Here we dig a bit more into the architecture of IMS. It has three different layers. It's the transport layer, which basically provides you the IP connectivity to your telephone. It has the control layer, which has all the logic you need in order to route calls, send them to a different user, send them to a TDM. And you also have the service layer, which provides you the ability to add value-added services for your operator, for your logic, for your business. The control layer is the core IMS. It uses a set of network functions, which are basically IETF protocols and specifications how to use them. You have SIP, you have diameter, you have MSRP, SDP, RTP, XCAP, and with 5G you also have HTTP 2.0. So you need to support this protocol and fine-tune them in order to create the interactions you need. And on the control layer, you have the proxy CSCF, which is the entry point of your phones. So whenever you place a call or whenever you turn on the VoLTE on your phone, your phone essentially sends a SIP register to PCSCF. This channel has to be encrypted between your phone and the PCSCF, so it uses IPsec for encryption and other protocols that we will be talking later about. But basically, the purpose of this proxy CSCF is to enforce security with the device, with your phone. There's also the interrogating CSCF, which is being used to, it's being used more like a load balancer on your core platform in order to determine which is the server that handles your services, your voice capabilities, in case you want to load balance them, because you might need to do that if you have like a big service. And this is the serving CSCF, which has all the logic for routing your calls. So it's the central node. It has knowledge about all the registered users. It provides the routes needed in order to terminate calls. Does billing information, authentication, authorization, everything. Basically, this is the brain of your platform. The HSS is basically a database that is being interrogated over diameter and stores information about users. And we've also got the service layer, which is somehow something outside IMS. Again, this is the value-added services that you want to provide to your subscribers, to your users. In terms of implementation, as I said, the proxy CSCF is the first. It acts as a SBC for your platform, provides secure channel between your devices, between your phone and the core network, uses different security mechanisms, the RFC 3329, IPsec tunnels or TLS authentication, and AKA authentication scheme, for those of you who are familiar with that. And in terms of media, it requires a secure RTP for communication or TLS for MSRP, for example. We've got, in OpenSIPS, this is quite easy to implement. That's because OpenSIPS is a SIP proxy, so it already has support for all the SIP signaling. It has the diameter interface that helps us provide the CX, DX, or GX or RX interfaces in IMS. They're very highly tunable, so you can use them in order to do whatever you want or tune them as you want. And it's very flexible that in case specifications change, and they do change quite often, you can easily adapt to the new specification. And also has been added IMS AKA authentication for mutual authentication between between the device and the IMS core. And we've also enabled voice over new radio because we've recently developed the HTTP 2.0 implementation in order to provide interactions with a 5G network. So lately you can also use OpenSIPS as a 5G IMS subsystem. But enough talking about IMS, because here we are at the WebRTC conference. What I also want to show you is, to present you is what ePCSCF. So this stands for Enhanced PCSCF, and is a component in the specifications that allow you to connect your browser to a subscriber core network. So this essentially helps you provide connectivity or get into a core IMS or operator's core network from a different device rather than your phone. This component has been introduced in 2013 or somewhere between 2013 and 2014, and it came along with the popularity of WebRTC. The mobile operator says, well, WebRTC is very popular, let's try to integrate it in our core network as well. And the goal is to provide unified services. So you have a browser, you have a phone, and you want to access both of them. You want to access the same services that the operator provides you. And the challenge is how to do that in a secure manner, because you don't want to, let's say, have an application that or anybody get access to your, I don't know, operator subscription, right? You have to do this in a very secure way. This is the architecture that the ePCSCF requires. So you have a web server. Here you have a WIC, which is basically a WebRTC application that is being downloaded from this server or accessed through this server that is able to interconnect directly through to the ePCSCF. So WIC stands for WebRTC IMS client, is this part, and it's basically a WebRTC JavaScript-based application that knows exactly how to communicate with the ePCSCF. It is downloaded from the web server and provides the logic and implements the APIs required by the specifications in order to access the IMS network. We've also got the web server, which hosts the WIC application, and you can get to this web server through, I don't know, the operator can provide you some credentials in order to get the application with your access credentials, but there may be different channels that you can get the WIC application. But as long as when you get the WIC application, the server needs to make sure that you also get the credentials to access the core network. Otherwise, it makes no sense, or you won't be able to access the core network. And from the SIP perspective, or the OpenSIPS perspective, it's only the ePCSCF which interests us, because this should act as a WebRTC to SIP gateway. The protocols doesn't say this W2 interface what should act, but ideally it should use SIP, or the specifications recommend to use SIP. That's because it's easier to implement. For example, you get an invite. You simply drop the WebRTC part, and then towards the I or SCSCF you use plain SIP. So this is MW is a plain SIP interface. So the role of the enhanced PCSCF is to normalize the traffic, whatever you're using on the WebRTC side. Whether you are using SIP, you can, for example, Janus can act also as a enhanced WebRTC, as long as you use this, as long as you normalize it to SIP towards the core network, you can have whatever enhanced WebRTC server you want. In OpenSIPS, everything is already available, so we didn't need to do anything. That's because already OpenSIPS is already able to operate as a WebRTC server, also secure WebRTC server. It provides AKA authentication that is needed for WIC to access the core network. And we can easily use RTP engine for media capabilities and media functionalities that are being used. So everything is already there. You just need to take them and glue them in order to provide, of course, and write the WIC application that enables the services you want. So in conclusion, I hope all of you already know or learned something about OpenSIPS. I hope you've learned something about IMS, what IMS is, and what IMS does, and you all know that OpenSIPS can act as an IMS core as well as an enhanced PCSCF in order to enable WebRTC support for your core. There's also, I was going to talk about OpenSIPS working groups, but I don't think I have time. Basically, I will say a few words and then wrap up. The working groups is a set of people, is a mailing list where a set of people trying to develop IMS stuff for in OpenSIPS. So if you have knowledge about IMS, try to register. It's open, it's free, everybody can access it, and it will help us develop a better IMS support in OpenSIPS. That's it. Thank you so much. If we have time for questions, I would be more than welcome. Tori?